Good morning, everyone. I'm Tianhang Zhang, the current president of Hong Kong SFPE student chapter. And today, I'm of a great honor to invite my friend, Mr. Xiuqi Xi from UCL, to give a seminar about his research work. And Xiuqi Xi is an expert in fire investigation. His research focuses on the microgravity combustion, fire spread, and fire modeling. And today, he will introduce some of his research work on data-driven forecast of fire. So let's welcome Xiuqi.
Thank you, everyone here. I think it is quite a while that I have been giving such official presentation here. It is quite a great honor and great pleasure to be here. And my topic today is about data-driven forecast of fire. And I believe that half of you are going to focus on this topic through your research area. And today, I'm going to give a very general overview about what we're going to overcome and where we're going to go there. Actually, that it is quite apparent or obvious that we need the fire predictions. You see that we have a lot of fires. And what I have participated in is the Notre Dame fire in France and the Grenfell Tower fire in Hong Kong. And I have collected a lot of witnesses and use some advanced fire modeling, just like the FDS or OpenFOAM, to simulate this fire. And the biggest problem is that during this fire accident, that the firefighters cannot really understand what's happening in such situation, because that we have the building. The building is designed in a certain purpose, and this purpose that we can refer that as a performance-based design. Well, that we need to think, what is performance-based design? It means that we have some regulations. These regulations or codes are from the existing fire scenarios. All right, for common buildings, just like this compartment, we have buildings, we have doors, we have ventilations, we have sprinklers. And here that we can say that in this situation, we can use this fire scenario. However, for a more complicated scenario, just like a very huge shopping mall, and something like the historic building, just like the Notre Dame fire, or very high-rise building, well, we have to say that these fire scenarios, they cannot, in the regulations, they cannot work anymore. So what do we need? We need a performance-based design. And it is where that the fire expert or the fire scientist come to participating, because that we need to understand the growth, the development, and the result of such fire. But is the performance-based design is the only way that we can deal with fire? I don't think so, because we need firefighters. In the real fire, what we have the fire scenarios in the performance-based design, they are idealized. That we assume. And I think that most of you have done a lot of simulation about FDS, right? So what is the HRR of All right. Oh, it's quite a pleasure here. So what is the HRR of in the FDS that you're going to use? 300, 500, or just alpha t squared? Alpha is from some codes as well. Well, I think that here that we're back to the regulation-based design again, right? In the real fire, then we cannot know or exactly know that what we're going to meet. For the firefighters, if they don't know what's going to happen, how could they deal with the fire? Yeah, just like in the Notre Dame, just like that in the Grenfell Tower fire, that firefighters just knock all the doors and leave the door open. It is a catastrophe, because in this high-rise building and in this kind of building style, there are a lot of doors. The compartmentalization of this building is so perfect, so the smoke cannot move so fast and so smoothly. But it is the firefighters that break the door and let the smoke get spread all over the building. The firefighters can never know that. But we are fire scientists. We need to know that. It's where that we need fire predictions. So from the literature by Howard Emmons, that the father of fire scientists, that he said that we need this kind of requirements or these required predictions. Just like that, we need to know the emergencies. We need to know the temperature and toxic gases, and the second here, I think it is main parameter that we extracted from the performance-based design. And then that we need to evaluate the loss, and then that we need to identify what kind of result that this fire can be. So this paper is written about 30 or 40 years ago. So can we make this prediction now? Oh, it seems that we have better understanding of the physics. We do a lot of experiments. We do a lot of experiments of different conditions, different environment, and this kind of different stuff. Well, we have better experimental descriptions. We even have better mathematical models and computational clusters. We can use the high performance computer to help us to deliver this. But I mean, can we, if there is a fire here, can we give a certain that, well, will the fire kill anybody? Or that for the simulation people, that we have the one common question: can you believe your simulation results? It is hard. Why is hard here? Because fire is complicated. We all know fire is complicated, but what makes fire complicated? Actually, that I do a lot of literature review and give a very deep thinking about that. Actually, that these times I spend more time on this rather than my own research stuff. And actually, that I think it is because of the because of the two reasons. The first is about physics. It's about multi-scales. And the next is nonlinearity mathematically. What is multi-scale for fire here? I think this one is kind of obvious. We have a lot of phenomena. We can see the phenomena. For the turbulence, if we dig into the Kolmogorov scale, then we can see that the time scale is about -3 power, and the length scale is about -4 millimeter. It is so small. And we have some scale that's even smaller, just like the chemical reactions. Think of that if the CO down to turn CO2, that the time scale is so small, and it will release a lot of heat instantaneously. And what about the radiation heat transfer? Then we have the spectrums. We know that the spectrum will give a lot of heat to different objects. And this change will happen in a much more smaller scale. But what we really face? We face condensed phase. We face smoldering. We face fire spread. That's the time scale for this condensed phase. It's about meters. And the time scale is about seconds. If we want to integrate this turbulence into this condensed phase, what we need is numerous computational costs, let alone for fire plumes. We have the buoyancy, we have the horizontal instability, and the real scale fire that we really want to solve, just like wide island fire. It's about hundreds of meters. How can we couple so many and so complicated phenomena into one model? And can we really understand this model? I don't think so. It is another phenomenon that is quite common in the combustion field or in any physics field. It seems that we always lack of computational resources. 40 years ago, that we have CFD, then we do simulation. Now we have much more powerful computer, but we still complain about that we don't have enough computational resources, and we can seek for the future whether we're going to have that. It is not the deal here. And what makes it more complicated is that the interaction between multi-scales. You cannot simply separate every single phenomenon here. Just like that, the most complicated, the example here is soot. We have soot. We have the soot agent, soot oxidization, and soot accumulation here. And the soot will reflect a lot of radiation, and such radiation will provide a brand new heat flux distributions to the chemical reactions. And these chemical reactions, again, to affect the soot. And finally, it will affect flame spread. If the flame spread is so fast that the room will get into flash over so fast. And it is something that we really don't want to see. Okay, so we have a lot of scales. Mathematically, how could we do that? Yeah, just like give an example about in the structure engineering, if we have the beam here. Firstly, that we compress the beam, then that we bend the beam. We have a lot of theories to describe this system, that we can separate these two forces and calculate the deformation of each force and then combine them together. This one can work. Why it can work? Because it is a linear system. However, what we face here is always the nonlinear system here. Actually, that this nonlinear system related to a lot of chaos theories and fraction theories. And this story began from Poincaré, that we studied the famous three-body problem to explain why the solar system is so stable. And then that we have our peer, the Lawrence. I have to say that we are peer because he's also in the numerical simulation of CFD, and he's the predecessor of such field. And then we have two mathematicians to try to solve this problem mathematically. And here that we can have the Navier-Stokes equation. Navier-Stokes equation is complicated. Why it's complicated? It is because this term here. This Vj here is the variable that we seek to find. This is the nonlinear term, and we have a very small, but we cannot ignore, but not negligible. That's the viscosity term. And this full equation produces turbulence and produce a lot of stuff that we cannot understand. And also that we have Arrhenius equations that for the chemistries and Steve Boltzmann equations for the radiation. As a result, these are from the mathematics, and if we see that from the physics, here that is the most well-known, that the temperature change with the column number. I think that it is about the emission and the extinctions. Actually, that we can define the point, and we can say, well, that we are, and conditionally that we can at this point. However, if the temperature change a little here, then we will ignite the field. We will ignite the field, and the gradients of such field fluid will change so sharply. It is what nonlinear is going to change from even from the numerical part. It is called the butterfly effect. If we have this very small turbulation, then we will see a very, very huge differences at the end. We have nonlinearity and we have linearity. For the linearity system, just like the case for the structure analysis, that we can separate them into different submodels, and then that we can add them together into the solution. The most wonderful and the most I think the most beautiful case here is a Fourier transformation for this Fourier equation. If we have an arbitrary initial conditions, we can separate these initial conditions into different waves, and we can solve these waves independently. Then we add them together, well, we solve the problem. But for fire and for any fluid mechanics problems, we cannot, because it is a nonlinear system. They are coupled together. It is because of the nonlinearity of the system. Also that we don't know the boundaries. So what are we going to overcome here? Multiscale from the physics, nonlinearity from the mathematics, and we have no idea what kind of boundary conditions that we need to know for our system. The problem is badly defined, and the technique is badly developed, and we have uncompleted conditions. And I think that it is not the problem for us. I think it is almost a problem for everyone here. Actually, that's the Nobel Prize given to the 3 scientists that study the complicated system. And it is quite a surprise for me because about 3 months ago that I talked with my friend here about some climate change and talk about this scientist, we call it the Japanese guy in Princeton University, and to see about his model about this kind of radiation and the volume simplification here. Actually, that these 3 scientists just represent every effort that we want to solve the complicated system. Yeah. He developed the method about the simplified system to describe how the climate change. And the middle one he developed the method that to use short-term prediction to give a long-term predictions. And the third one is in quantum mechanics. He's the expert in normalization, and he wants to use several particles to give the whole descriptions of the complicated system. Actually, that's from the interview of Xiuqi, he said we must always simplify. We cannot compete with the complexity of the nature. There is no much physics involving raindrop that would never possible to compute absolutely everything. It don't fire us with. We need always simplify. We cannot compute everything from chemistry, from radiation, from soot, heat conduction, heat convection, and real-line fire. So my topic here is that because it is a whole map here, what I want to pick is the near-world flow here, because in the field of fluid mechanics and combustions, it is the area that is so typical dealing with these complexities. And here that it is a picture, it is a realization of the one-phase flow. It is not combustion, it is one-phase flow. The Reynolds number is not so high, to be honest. It is about 400. And in fire, I believe that it is much more greater. You can see that we have turbulence, we have multi-steps, we have the very sharp gradients here. So we want to make what we really face here is that we have a lot of stuff like this, just like this. To give an example in another field, just like that in the structure of fire protection, we need to know what really this fire gives to the element. And we need to calculate the heat flux here. The heat flux is dealing with the turbulence flow here. We will never now, I have to say now we have no ideas and no method to calculate this one. It is catastrophe. But it is a catastrophe, but we still have some philosophies that is potential to solve this problem. It is self-similarity. So what is self-similarity? Self-similarity is, I think it is the only method, and it is a very ordinary, but it is kind of the powerful method that we can deal with such complicated system. Actually, that we have seen a lot of equations. These equations have a lot of parameters, just like Hooke's law, that we have the Young's modulus that we can relate to the strain to the strength. And here that we can see that the Young's modulus will be a constant in the elastic region. But outside of the elastic region, that Young's modulus will change. It means that inside of the elastic region, that we have the self-similarity, but outside of it, we don't have it. And here that we have the Newton's law of shear stress, we have viscosity. We know that the stress is proportional to the gradients of the velocity, but we have non-Newtonian fluid. This way it cannot move. And we have dimensional analysis. We have a lot of proof model. We have the most famous and most powerful cosmograph -5/3 law. Yeah, it is beautiful. This whole theory is so beautiful from the dimensional analysis and this kind of self-similarity. And also that from about 100 years ago, there's the boundary layer theory that we have the exact solution from the Blasher solution. We can see that the Blasher solution is essentially a self-similarity profile as well. It is not in the field of mechanics. It is Maxwell equations. That's electromagnetic waves. And for the molecule dynamics, we still need this similarity. Why to help us to simplify the problem here. And such similarity mathematically, and such similarity, how can we implement this similarity that we can use that to some transformations. And with these transformations, that kind of I don't know, but possible, some results can be get. And here that we can see how many parameterizations and how many similarities that we can use in this diagram. We will have chemical reactions. We have Arrhenius equations. We need to think that, well, we have to think that for the complicated reaction forms that we have self-similarity. Their equations come to similar to each other. For the turbulence, that we have eddies. And for the soot formation, we have to think that, well, the soot formation will accumulate in a similar way. And even for the convections, for the Blasher solutions, for the pyrolysis, that we will think that, well, the thermal wave it has a propagation. So the waves is kind of similar to each other. And mostly for the Planck spread, we will see that, well, for the Planck spread, we will assume that the shape is similar to each other. for the 5 problems, we have Hesper model, we have Xiuqi model. They are all based on the dimensional analysis. And even for the real scale fire, just like the compartment fire, that we can refer a lot of dimensional analysis work from quintillion to see how this one is so powerful in our field. And here that it is kind of interesting because the self-similarity is a physical concept. It also have another, mathematical concept. Why? Because the complicated system can according to the differential equations with the infinite coordinates. See that we have the system here, we have turbulence, we have multiple degree of freedom. And for and accordingly, for the differential equations that we want to describe the system, we still have infinite variables. We need parameterization to make them from infinity to finite stuff. And here that we have physically that we have the system with some domain physics, just like for the Planck spread, we will focus on the heat and mass transfer. For the smoldering, that we're going to focus on the porous medium heat and mass transfer here. And here, mathematically, that we're going to have some several differential equations with finite freedoms. And then that we want to solve this system. Mathematically, that we're going to use dimensional redundancies and it related to some mathematical concepts just like the group theory. And in physics, that we will find the similar profiles. Here, that if we have the similar profiles, that we have the dimensional stuff, that we have the problem here is that what kind of scale that we need? We know that we have the similar profile, but how could I do the transformation? It's just like that. It's just like that. We know the flame temperature or the temperature profile get higher and get lower. So what is the real scale here? Well, I think that it is really hard problem now because this one is related to parameterization. What is parameterization and these kind of similar profiles really contain is numerous small scale physics. It is only the experiment or the observation can help us. So data-driven is not just the technique here. It is I think it is almost the only method that we can fight with the multi-scale and nonlinearity problem here. Firstly, that we have observation. Then we use this observation to help us identify what is the scale that we're going to use. And with these proper scales, that we're going to make predictions. So I think this one is what we're going to do here. I think that this one is kind of familiar to part of you. It's just like that we have some variables, and then that we have some forward model, and then that we have some observations. If we have the observations, then we will do the inverse model here to help us to identify the parameter here, and then that we can put forward to give much more predictions here. And here that for the forward model, that we can use FDS, we can use impaired correlations, we can use a lot of forward model. And for the observations, we have something like the geometrical properties, just like use a camera, or some statistical properties, just like we can use the thermocouple to do that. And for the inverse model, it is something that we can put a lot of techniques. Just like for me, that I use the minor search and gradient descent method here. And most probably that they come to use something like the machine learning and the smart algorithms here. But what I want to emphasize here is that what's really important inside of the loop, I believe it is the forward model and the observations. If we cannot have a proper forward model, we will never get the profiles. It means that if we don't have proper similar profiles, then we will not get the real scale. If we cannot get the real scale, how could we compare the result of the forward model with the observations? And another thing that is important is that we need better observations. If we have the really bad observations, or the observations have the great variance, or the observations is totally different, it's totally different from that what we want to get. How could we compare the results of the forward model with the observations? If we have the forward model and the observations, the inverse model that is considered a minor part of this work here, because that's we need what we need to do for the inverse model is that we want to compute the parameter faster and more precise. Only that we can have the proper forward model and observations. Can we discuss the problem that we need in the inverse model? The forward model and the observations, they are prerequisites. So what we need now? What we need is better models and better measurements. So it's related to my work about 3 years ago that in UCL that I've tried to develop models of the better model, and here that with the help of the Fire Lab that I can realize some of my idea and try to deliver some better measurements here. And I think that in this part, what I want to extract is almost done, so I could give a very quick view that what I going to do for these models here. Actually, that it is a review to search about what kind of the forward model that we have here. The conclusion is that I need to develop my own model. So I want to start from the symmetrical droplet flame spread, droplet combustion to the two-dimensional diffusion flame, and then to the large-scale fire. Why I want to start from the droplet combustion? Because it is a convective diffusive system that is quite typical for fire, right? So my first work is about this physical process. That the new workflow, it is always the most problematic and has the most uncertainties here. The best principle is that, well, we know that this region have a lot of uncertainties. Why not just put some similar profiles inside of the region and only let the CFD region outside to give some boundary conditions to this region? So I put this model here. This one is the interface, and inside of the interface that I use the classic droplet combustion model analytically to calculate the near wall region and the condensed phase region. And outside of the interface, I implemented the CFD model to give the hydraulic environment for this droplet combustion here. And in this way, that the boundary conditions and the scalar and the vector exchange there at the interface is kind of important. But this one is kind of complicated. I think that you can refer that in my manuscript in the combustion symposium here. And here, the one I choose is two parameters. Is the C in from the droplet combustion from the droplet size from the D spiral and the Spalding B number. So if I choose these two parameters, that's the inverse model. That's the data-driven model can be completed here. So we have the forward model. We have observations. The observation is from the International Space Station, and we can have the observation by compare them. But we can have the loop here. And all the source code and input files, they are all online in my GitHub. It is free for download. It is for free for everything. So you can search that. Actually, it is some results that I get here. And the first one is the droplet evolution, and the next one is the flame length. They are all geometrical. They are all geometric measurements. Meanwhile, that I can have some other measurements, just like the temperature of or the species concentrations here. It seems that, well, it more or less can work, but not good. And actually, that when I move that into the droplet combustion with the buoyancy, I almost get the similar result. And it is in the same work shared through the microgravity combustion here. After I doing this, I got to dealing with something like the real fire here, the flame spread problem. Flame spread is is not one of. It is the most important topic that in the fire, because the flame spread will decide the fire size, and the fire size is always that we want. And fortunately, that I get involved in the Fire 4 project. That is the fire that's the fire that's conducted in the space. And this experiment is conducted last year. And what I did for this project is do some very simple data acquisition steps. And different from the droplet combustion for the two-dimensional flame spread problem, that it is much more complicated. But the philosophy behind it is kind of similar to each other, is that we still don't want the near world region. We still need we still want the CFT to calculate some hydraulic conditions inside of the system. And more important that we have a totally different condensed phase here. And here that I divided that the region into the whole computation domain into 3 regions. And firstly, that I want to use the Amos problem to use the boundary layer theories to calculate that the mixture fraction. This one is mixture fraction, and this one is the velocity field here. And in order to, because for the exact solution, I'm going to need a lot of iterations. So I have to give some simplification here. Because this one is kind of important. The two most great simplification is that I use the von maximum integral here, and I use the linear density profile here to give me an explicit solution. And for the condensed phase, it is quite known for the continuous model that a typical solution here. And actually, that there are a lot of things they're missing here, just like the boundary conditions and some justification that how could I use this model and why this model can work. And more details will be found in my another paper, and I hope it will be online soon. Yeah, this one is the boundary conditions here. And here there are some very preliminary results here. So the biggest problem here is that we still have a lot of problems. That in the droplet combustion, that I choose the spotting B number and the condensed phase number here. So following almost the similar methodology here, but what I want to put here is BP to C1 to adjust the condensed phase. Another thing is kind of tricky here because I need a parameter that wants to control the gas phase here. So I make a very broad assumption here because what really makes the spotting B number really complicated here is that spotting B number essentially is the heat transfer balance at the field surface. And the heat loss term is still a big problem here. What I make a very broad assumption is that this one could be a constant. Then I put another C2 here. And this one shows that if I choose different parameters, that whether this curve comes to collapse into the same curve here. And the result is kind of great enough. But if that's true for every parameters, it doesn't. Especially for even the stoichiometric ratio is kind of so low that the flame cannot formulate it. So you can see that we can only get a very low curve here. And here there are some results from the pyrolysis length and the flame length here. But we can see that this one is kind of work more or less. But for the flame length here, there are still a lot of problems. I have to say that I think it is 50% of the problem can be caused by the experimental observations. It's not bad, but not so good, to be honest. And also that for the discrepancies here, it implies that maybe that we need a third parameter to control the chemical reaction and the trading. Because for the flame spread problem, that's the trading. How could we define the flame length here? That we have the visible flame length. That's the chemical reactions happening at the trading edge. Will certainly relate to chemical reactions. But in my model, what I use is one-step chemistry. So I think that this way, a third parameters may be necessary or not. And here the light I don't know, yeah, but I stop for the microgravity combustion because in this case that it is too expensive to do the experiment in the space station. And I have to say that we have several unpleasant stuff with them. So I have to move to the buoyancy case. And with the buoyancy that we have a lot of detail and a lot of more experimental descriptions here. Well, almost follow the same methodology here, that these two equations describe the flow of the boundary layer combustion in gravity. And this one is also the continuous model. And for my CFD model, that I also have to adapt the low Mach assumption to give you the simplification. And the difference is that the net burning rate is proportional to x power 1 over 4 here. And also that for the first step, I still need to assimilate C1 and C2 and see what's going to happen here. And this one give me a C1 and C2. They are not so beautiful as previous steps because this one is doing work here. And fortunately, we can still see here that the plan length is still underestimated. So it implies that well, we still need the third parameter here. And if we have the data, we can try to find the third parameter. Now I think it's down column number to give us a more detailed descriptions here. And then when we look back into the system again, so could I make sure that whether I have a better model? I don't know, to be honest. There are still a lot of things that need to be done and a long way to go. I think that I solved the problem of the droplet combustion, partially kind of solved the problem of the two-dimensional diffusion flame, but what for the real scale fire? I don't know. I think it is science. And another thing that I want to emphasize is that, well, I have the model, but what about the measurements? What I want to really measure here is that from the previous model, that's one thing is literally repeated a lot of times is the heat flux. It is the heat flux that communicates the gas phase and the condensed phase here. And what's the model that I use for the boundary layer combustion? They have a very, very, very strong assumption for the boundary conditions. It is a Stalling B method. The mass flux is proportional to the gradient of the temperature and the gradient of the species contractions. And this is connected by B here. And B here, and B that's the scale of the cell similarity profiles. And I'm wondering, because this one is assumption, and it will just directly affect my boundary conditions for this problem. So what I want to see is that whether I can find some way to explicitly calculate this one. So the first thing that I want to use is the wind tunnel. I modify the wind tunnel, and I want to use some anti-qualitative analysis, just like to take the gravity as a prevention, to study whether I can get some useful results for that. But I have to say that the experiment and the analysis, they are failures. Because in reality that the camera is not so powerful, maybe some high-speed camera will work, and also that the physics that happened in the real theory and happen in real life, they are totally different. So it is hard. The next thing is that I want to try to use some cylindering stuff to help me to realize the flow. It's also a failure because in the cylindering, it can only provide some very coarse or some picture for that. It cannot be used for some numerical stuffs. And then that when I think about other measurements here, that I list a lot of diagnostic techniques for fire, including the pointometer, thermometers, the flux gauge, also that's infrared, these cameras, and for the solid tests, and we have the TG and ODSC here. The biggest problem for this measurement is that they are all integral measurements. What they measure is average, or the temporal and the spatial resolution of such measurements is kind of low. Because what I really want to understand is the surface physics for that, especially for the gradients. So I need to find a new method to dealing with that. Actually, that's the combustion diagnostic provides a lot of useful tools here, including the intrusive or non-intrusive stuffs. For the non-intrusive stuffs, they are partially spectrum-based or partially non-spectrum-based. And for the non-spectrum-based, that they are PIV or LDV. They are measuring the velocity here. Yeah, but I want to start from the temperature. So I just add this to stuff, and I've tried cylindering, it's not so good. And for the spectrum base, that there are 3 potential spectrometers that could be helpful. Infrared absorption, or really with the spontaneous Raman scattering here.
Actually, that's what I choose is the Raman scattering because there are a lot of deficiencies in the infrared observations in this situation. And for the intrusive technique here that we have thermocouples, that we have the chromatography. Yeah, I'm happy to see a brand new device here. Also some nice spectrometry here. But I think that's for the intrusive one that it will greatly affect the flow pattern. And for my situation that I want to really study the heat flux near the wall, it is not ideal. And here, what I've done is the Raman scattering for the liquefier here, and I designed the stuff here and played with that for a very long time, and then that I get some very preliminary results here. Yeah, what I intended to do is that, well, what I really want to have is the heat flux or the temperature gradient, both at the gas surface or the liquid surface here. For the gas surface, it will measure the time differences and divided by the delta T. And for the gas phase here, that we have the energy balance here. Is that input, that's the gas input will be used to get inflation and also to deliver heat. And also different from other kind of field this field going to evaporize instantaneously. So I have to measure two different stuff here. And this one is a Raman spectrum with the different liquid temperatures here. And we can see that with different temperatures and we can have different Raman spectrums here. And this peak is for the CH band here. And by identifying them, and I hope we can get some useful results, especially for the liquid temperature profile. And I have measured the temperature, and I have measured the flame. I've measured the spectrum here, and the data processing is still in progress. So yeah, it is not a story compared to the internal subject stringering. This one is kind of more promising. And the biggest problem that I need now is for the gas phase. For the gas phase, that the intensity of the gas phase is kind of so low, different from the condensed phase. And the flame emissions will also emit a lot of flames that have the visible light. And also because I have to deal with this such low intensity stuff, I need to do some related post-processing stuff. Yeah, actually that when we look back into fire and the development into several hundred years, then we will see that we are all firefighters. What we fight is fire. But what kind of tool that we're going to use? We have computers, we have pencils, we have computers, we have a lot of devices. But I believe that's the most powerful tool is the understanding of the world. It is the physics that are going to help us to control these physical stuff. We have mental stuff, we have physical stuff, but the physics is the weapon that we need to manipulate. Yeah, I will give my gratitude to Professor Asmani to give me an opportunity here. And also I want to thank my supervisor, Professor Terrero, to let me to play with this kind of stuff and give me a lot of free chances and free time. And also that I want to thank Chu Tianwei because that we spent numerous time in the lab to assemble such crazy stuff. Yeah, and I also want to thank all of you here, to the colleagues and everyone that I meet in Hong Kong. So this fire is, I think this fire is by Arab, right? This is by the staff of Arab to give a demonstration of the Great Fire of London here. Yeah, we still need to fight it. We need to fight it, and it is our responsibility to use physics to fight it. Thank you, everyone. So I think it can start a seminar. I'm open to almost all kinds of questions from different field and different aspects, not limited to this kind of presentation. Yes.
Could you please move to the page which contains the further model?
Further model? Yeah, just tell me where to stop.
Because this part it contains two parts. I think it
as traditional methods and also some machine learning and deep learning methods. But you mentioned you need the data-driven method to solve these problems. But as far as I know, the traditional methods doesn't need so many data.
Yeah. But the biggest problem is that do you need data? Definitely that we need data. So what's the difference between the traditional and the contemporary?
I think the traditional method we usually need to conclude some mathematical laws to explain some phenomena. But for the machine learning and some artificial intelligence methods, we just use a lot of data to let the machine to predict the ones.
Yeah, the biggest problem is that can you abandon forward model?
Of course not.
Yeah, of course not. So if we don't have FDS, we are about 30 years ago, that we have we're not so powerful FDS, that we don't even have computers. I give you several imperial correlations. Could you get the same results?
So I just wonder which method you apply in your research.
Binary research. The most simplest.
Okay.
Yeah, because I think that because what I want to emphasize is the limitation of the forward model and how could we get the better observations. I mean that if these two are perfect or they can coordinate to each other. So even the simplest algorithm could get it.
So I got a question.
Yeah.
What is the core idea?
On my data-driven core idea is that we think that we need to develop a simplified model for data-driven process. What is simplified is have two steps. Is that we need to keep the balance between how much physics that we need and how much simplification we need to apply. We know that for the FDS we have a lot of simplifications, but these simplifications they are implicit, right? Yeah, just like in FDS that we have low mass number, we have one step chemistry combustion. Yeah, we have the different radiation model. We can put a lot of parameters, just like the emissivity, HRR, alpha, this kind of stuff. They are all based on the physics, and they have all the physics here. The forward model that I want to search or I want to develop is that how could I keep the balance between the physics and the simplification? Because some physics is not we want, right? Just like the radiation. The radiation fraction is about 30% of the total energy, is more or less the same. But some simplification that we cannot abandon, just like the flow pattern or the heat transfer inside of this condensed space. We need to identify them. We need to identify them, which part of physics that we need and which part of physics that we don't need. It is the core part. It is not about the results. I have to say that this model is not perfect at all. Yeah, but we need to do this kind of stuff. Yeah. Yeah, actually, that's the biggest problem is about the flex spread. Could we? Yeah, I think that we all identify that the flex spread is the most biggest problem that we can find. Why? Because that we all use FDS, right? So in FDS, that the most significant input is the heat release rate, right? If we don't have any heat release rate data, that we cannot produce any simulation for that. But for the heat release rate, we always have two options. The first is that we have the stable heat release rate, or we have the alpha T squared fire. For the alpha T squared fire, that we assume that the flex spread is a constant. So that the fire get propagated radically, just like in a circle. And in this way, that the flex spread is a constant. And then that we have alpha T squared. But in real case, that we not always like this, just like that if we have the vertical fire, that the alpha T squared fire cannot work anymore. So the flex spread rate is the core part to calculate HRR.
And it is why that even from the beginning of the fire science, a lot of people, even though that's the flame spread phenomenon is studied about 50 or 60 years, we still have a lot of people put a lot of experiments and a lot of simulation in that, because we need to find a method to help us predict the flame spread rate. And here, what I want to do is that try to use data assimilation method and this kind of model to give a prediction about the flame spread rate. With the flame spread rate that we can calculate HRR, and with the correct HRR, can we calculate the real phenomenon inside of the compartment?
So about the laser setup, so it seems like it's best to measure the temperature in the condensers. So can you do that? Cannot do that with temperature.
Yeah, actually, that I have to say I don't know. Yeah, it is a hard problem because
of the noise is too big.
Yeah, because of the noise. I mean that for every combustion diagnostic techniques, that's we need to know where the noise comes from, right? The noise is always is from two parts, as I conclude. The first one is the spontaneous emission of the chemical reactions. Yeah, just like the chemical reaction will emit different wavelengths of the light. So it is something that we need to solve. The second one is the soot. The soot will give the scattering for that. And also it is the reason that I choose Raman scattering rather than the infrared absorption infrared technique. Because for the Raman scattering techniques that most of the particles of the soot is from the radius scattering or the mean scattering. And the wavelength is identical to the input wavelength of the laser. And what Raman scattering really measure is the wavelength bigger than this wavelength is kind of bigger. So instantaneously, it will filter out a lot of noise from the soot. And for the first problem is the spontaneous emission here. In the infrared, it is still a big problem because the chemical reaction will also emit some infrared lights. And here, what I only think is that, well, maybe some average method could be used. Also that a lot of new techniques based on the Raman scattering, just like cars, coherent anti-Stokes Raman scattering, they more or less to overcome the deficiency of the spontaneous emission, but the expense of such device is so huge.
So you haven't set up years. So what can you do?
Yeah, to measure the flame temperature to measure the flame temperature to give me the heat flux profile and help me to understand and help me to answer the question: will the boundary conditions proposed by Amos is correct or not?
Yeah, but right now it seems like the noise is too big to so
yeah.
It can be dedicated for measure.
Yeah, it is hard, but I think, we need, but it is for the liquid. Yeah, actually, that I get some signals from the gas as well. But compared to the liquid, the intensity is low. Maybe I can adjust the light path and have a more sensitive receiver rather than the thing that I made my own self. Yeah, to help me to increase the intensity, because the cost of such device is kind of low enough. It almost like a demo. I mean that in a demo that I can observe as some spectrum from the gas. I think that if we can have some better camera, that such stuff could be solved, but I cannot give a certain.